Hello, Mr. Aaron, Mr. Ryan, are you right?
Yeah.
Okay. So we're given a positive integer, and with one operation we can add or subtract any power of 2. And we can do this as many times as we want. And the question is, what is the minimum moves to reduce the number to 0? For example, the 7. We can do 7 minus 1 minus 2 minus 4 equals 0. That means a 3-step. 1 to 4 are all power of 2. We can do this 7 plus 1 plus minus 8. Sorry?
Why do you always use 7?
Because that's a very good example. Look, 7 plus 1 minus 8 equals 0, right? We only need 2 steps, so this is the minimum. On the first day, we talk about finding the closest number of 2.
No, on the first day we talked about recursion.
Yeah, recursion, actually, Fn, we want to calculate Fn, the minimum number of steps to bring the n to 0. And we just need to look to 2 cases. One is the closest to, because there are only 2 closest power of 2, right? So Fn minus 2 to the power of a, or F2 to the power of a plus 1 minus n. Alright? So this is the binary tree. And on the first day, we talk about recursion. We need to evaluate these 2 cases. And we also talk about the greedy, which is just picking the closest to. Also, we talk about this. When you look at the binary, for example, like 7 is 0, 1, 1, 1 in binary. And if the last 2 bits, the least significant 2 bits are 1, 1, a much better way would be to add 1. So if we add 1, that will become 1, 0, 0, 0. And then we can remove it, which is 0. Okay? So we follow the strategy. If the last 2 bits are 1, look, n3 equals 3, then we choose to increment 1. That takes 1 more step. Otherwise, we remove the least significant digit. For example, if it's 0, 0, 1, then we just remove the least significant digit. And if this is 1, then that means 1 step. By looking at the binary, like 10, which is 1, 0, 1, 0, because 10, this is a, this is 2, right? Okay, so how many steps? 10 equals a plus 2, a plus 2. This is 2 to the power of 3, this is 2 to the power of 1. So each bit, each one in binary is power of 2. So the obvious way will be just removing each one. If there are n ones, then that takes n steps. So today we're going to talk about using the breadth search. We talk about the breadth search to solve many problems, and we can visualize these. We can solve this problem using the breadth search. What is breadth search, by the way? Breadth search. Can anybody explain to me?
Line by line.
Line by line, yeah, breadth search. So search tree, right? Search tree. So breadth search. 1,
2, 3, 4,
2,
5,
3, level by level, yeah, level by level order. So we use the DQ, double NDQ, to implement this breadth search. Am I right? Yes? A queue. Put a root in. Okay, now when the queue is not empty, we take 1 out. When we take element out of a queue,
Queue is usually defined as a braid of hair worn hanging down behind. As a verb,
stop!
queue is usually defined as to
Alexa,
wait
stop!
while waiting, often followed by a
Alexa, stop!
ask.
So DQ is taking out the element from the left hand side, right? First in, first out. Just imagine you want to buy something, you're waiting, you're queuing in front of a shop. So you see first in, first out, right? So this is the shop. And when we have more customers coming, so we queue on the right hand side. And the next to serve is from the left hand side. So first in, first out. Okay, so we put the 1 in. Now the next one to serve, to be taken out from the queue is 1, right? Taken 1, so we have 1 here, order. What's the kit of 1? 2, 3. So we just put 2 and 3. So what's the next kit to take out? What's the next customer to take out? 2. Take out. When it's taking out, it's being served. It's being visited. 2. What's the kit of 2? 4, 5. Put it at the right. What's the next to take out? 3. What's the kit of 3? 6, 7. So put it at the right. What's the next one to take out? 4, right? Is it 4? So 4. What's the kit of 4? Nothing. What's the next one to take out? 5. What's the kid of 5? Nothing. What's the next one to take out? 6. What's the kid of 6? Nothing. What's the next one? 7. What's the kid of 7? 8, 9, 10. Right? Okay, and then 8, 9, 10. So look the order 1, 2, 3, 4 up to 10. So this is the breadth search order. So how can we apply this breadth search to solve this problem? So we can imagine this is basically a search tree problem, right? Search tree problem. So for example, like let's take a look at the example 10. Okay, the root is 10, right? The fn, this is n. 10. So how many next step?
2.
Okay, yeah, it's 2, but we are talking about searching, right? To just what's the next possible moves? Could be a lot, right? Brute force.
Yeah, that's just.
What's the power of 2, right? 2 power of 2 is 1, 2, 4, 8, 16. This goes on, right? So this one will be 10 minus 1. This one will be 10 minus 2. Yeah, I know. This one will be 10 minus 4 and goes on, right? You can minus and also you can do the plus here, right? This is the entire search tree. This is kind of like brute force.
Yes.
Yeah? Does it make sense? Okay, because there are unlimited number power of 2 and we are given this n. Let's say this n is smaller or equal than 10 to the power of 5. Okay? And we can pre-calculate
That's
this.
still a lot.
I know it's still a lot, but there are 31. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 31. So there are 31s. So we can say power of 2 equals 2 to the power of I for I in range 32. So this is known, right? So this is kind of like branching factor. We know these are the power of 2. And for each kid, we can expand the search tree. Expand the search. Oh, obviously, if we've seen this number before, then we don't expand it again, right? So in order to do that, what kind of data structure do we need to use to remember? Set. Yes, we're using the set to remember. So for example, like 9, this is the first time. Then we expand the tree. We put the node in the queue. And the next time, for example, like, look, this is A, right? This is A. 10 minus 2 equals A. But A could be A plus 1, right? Here, look, we have another 9 here. So, but we don't continue because we have visited the 9 here, right? Does it make sense? This is breadth search. Why do we use the breadth search over the depth search?
Because it's more.
When we talk about breadth search,
simple. It's more better. More efficient.
okay, what's the difference between breadth search and depth search?
Depth search, they have different names. Depth search goes as deep as it can, but breadth search.
Okay,
I think breadth search is more easy to understand.
to understand. Depth search is also understand. So
No, you can. It's more simple.
both are simple.
No, but it's simple for you, but for a beginner, breadth search is more
Okay. So
simpler because you just line by line. That's just easy. Then
Yeah.
go deep, then blah 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 blah.
okay, so let's say I want to find the shortest. I want to find out the shortest distance. Which accurate is more suitable? If the question is asking for the shortest distance, then the breadth search is the way to go. Because look, if I find a 6, this will be the shortest. Am I right? But depth search may not be the shortest. For example, like if I have another 6 here, if I want to find the target 6, breadth search, level by level, this is the shortest, obviously from 1 to 6, the shortest. But depth search, you might find this one. This is not the shortest.
Oh.
Yeah?
Okay. I get it.
If you perform the breadth search, this is the shortest, right? But if you perform the depth search, find this 6, this is not the optimum. Unless we perform the entire search tree, brute force the search tree using the depth search, and then we find 2 6 and then we compare. This is 6 is the minimum. Make sense? So this one is breadth search because we want to find out the shortest distance between 10 to 0 here, right? 10 to 0. So for example, like if the first time we find it here, 10 to 0, some nodes, 0, then this is the shortest. Am I right? Does it make sense? But if we perform a depth search, this might not be the shortest because if I'm here, then there might be a zero quicker way. Make sense? This is the difference, core difference between depth search and breadth search. When we talk about shortest distance, okay, so if the question has this keyword, shortest, minimum, breadth search. If the question is talking about, is there a way, is there a way to do this? Is there a path existent? Then we're talking about depth search because we can stop the depth search as soon as we find a path. Okay? And the performance-wise, the breadth search needs to store the branching factors in the memory because look, it needs to keep a list of the children nodes in the queue, right? This is the space complexity. But for the depth search, it only needs to remember the path, much less space usage compared to the breadth search. And we also talk about iterative depending search, which is the combination of depth search and breadth search. Remember, first of all we set the max step to 1. If we can't find it using the depth search. So basically at the beginning we set the max step to 1 and we perform a depth search. But when we exceed the depth limit to D, then we just stop, right? Hard stop. We don't find it. Then we increment the D. We perform a depth search. Do we find it? No. Then we continue. Keep incrementing the maximum depth. Okay? So this is the combination of breadth search and depth search, and it combines the advantage of both approaches. Okay, so coming back to this, we can use the breadth search to do this, to find it, right? But we need to remember the numbers. For example, this 9 has been visited, has been seen before, and the next time we don't expand it to the tree. By looking at this search tree, I mean, it could be huge, right? So the time complexity will be much more than the previous approach. Remember, the top-down dynamic programming recursion, we're using the cache because each n has been calculated exactly once, right? So, but this one, the search tree could be huge because the branching factor, the maximum number of kids in a tree, which could be 16. If there are 32, okay, so this is 31, right? Okay, so if there are 31 power of 2 to consider, there will be 31 times 2, 62 kids for each kid. Am I right? Why is it 62? Why do we need to times 2? The maximum number of trial nodes for any given node in this search tree could be 62, up to 62. For example, if given the root 10, then the kid next one to consider would be 10 minus 1, 10 plus 1, 10 minus 2, 10 plus 2, 10 minus 4, 10 plus 4, 10 minus 8, 10 plus 8. Okay, and they are 31. So each one has plus and subtract. So that makes it double, which is 62. Binary tree, which is 2 kids, right? 2 kids, binary tree. 3 kids, what do we call it? Trinary tree, right?
Yeah.
Okay, so this is 62. So it's 62 n-ary tree, okay? 62 n-ary tree, so it could be very huge. What's the DQ, by the way? Double NDQ, yes. From push and pop supported on both sides in O1 constant time. Define Fn. If n equal 0, then return 0. Q equals dq. At the beginning, we put the n, and the number of steps is 0. Sin equals set. We need to use the notebook hash set to remember the number we have visited. While q, the current number a, and the distance is q dot pop left. So we take one node from the left hand side of the queue. We take the number and we also know how many steps so far, how many operations we have taken so far, right? If a equal 0, so if we have reached the 0 at any time, if the number is 0, so this is search tree, right? So if any time this number is 0, then we find the shortest path. And then we know the distance as well, because every time we push the node to the queue, we update the distance. So if a equal 0, then return d, right? Otherwise, look, if this is power of 2, okay? This is power of 2, let's call it p. Then we need to go to each power of 2 for x in p. P is power of 2. for each x, we can do minus x and plus x, right? So for nx in a minus x, a plus x. If nx not in scene, right? If we haven't visited this number, the new number, then first thing to do is we put it down on the notebook, sim.add nx, and push it back to the queue, in queue on the right hand side. So it will be q.append on the right hand side, which is nx, and the distance should be updated to +1, right? Because it takes one more step. Make sense?
Yeah.
Okay, so one problem here is that, look, this could be very slow. If the given x is smaller or equal than 10 to the power 5, then at any time, if the distance to the original is more than that, we can just ignore it. We don't need to consider, am I right? So we can add a criteria here. And if the distance, ABS distance, the nx, if the original distance, what's the original number? Minus a, right? If minus a is bigger or equal than 10 to the power 5 or anything, right? If we have gone far, actually it's the opposite. The distance is basically saying that if this 10, right? For example, 10 minus, do we need to consider 10 minus 2 to the power 31 or 10 plus 2 to the power 31? This become very small, this become very large. It's unlikely to find a minimal answer through that path, so we drop it.
Yes.
2 to the power of 31 is very large number. Okay? For example, like 10. We know the minimum, the optimum path is 10 minus 2 minus a, right? Here we're saying that, okay, so because we have to try 2 to the power 31. So do we actually need to try 10 plus 2 to the power of 31?
Mm-hmm.
Why is that?
It's too big.
It's too big, yes. It's unlikely to find the answer, right? This is common sense, right? In theory, there are 62 kids, 62 possibilities each part. But we're just saying, okay, for those too big or too small, we don't need to consider because it's unlikely to find the answer because look, this 10 is so small, we don't need to consider 10 to the power of 2, 10 minus 2 to the power of 31 or 10 minus 2 to the power of 30. This is actually a very huge number. There's no point to try. And we can just ignore the past and make it simple. So we add the least to only put the kids which are likely to find a minimum, okay, into the queue. We talk about recursion, we are finding 2 closest power of 2. This one is different, right? This one is slightly different. It's finding the next possibilities. What I mean is next possibilities that +1 minus 1. This is considered in one variable. +2 minus 2. +4 minus 4. +a minus a, right? Okay? Yeah?
Yeah.
But the first lesson, the recursion. Remember that 120. For 120, what's the next move in the first lesson? The first lesson will be finding that 64 and 128, right? Only 2. But today, the difference is that today 120 is not finding these 2 numbers. It's finding 120 minus 1, 120 plus 1, 120 minus 2. The nodes to expand are more than this recursion. This is the brute force. So we don't actually need to prove it mathematically. But in order to use the recursion, only solving these 2 nodes, we need to prove it using mathematics, which you have covered in the previous lesson, right? Yes? And also we talk about the recursion, another recursion form in the last lesson, divided by 2. Fx, if it's an even number, is equals to fx divided by 2. If it's an odd number, it can also be reduced to half of x. Okay? So what have you learned today? And what's your biggest takeaway? Come on, guys. Eric, want to say something?
No.
Eric, can you say something? Eric, say something.
I don't have a tractor, we have a tree.
We added number and we want to try the minimum time by adding or subtracting a power of 2, and we want the minimum amount of time we could do to 0.
Solution is that we have this tree and then we
breadth search.
which shows all of the possibilities, not all of them, but in a certain range, and then you have to pick one, and then yeah.
Okay, so how do we avoid the duplication? How do we avoid that?
We use set
Yes. So why this approach works?
because it just works.
Why we can't use the depth search here?
Depth search.
Why can we not use the depth search here?
Because it will take more time, because it goes from left to right, and then if it's on the right, then it'll take a long time.
Let's try, yes. Because depth search is not suitable to finding the shortest path, but the depth search is suitable when you ask it for like, is there a path? Can we reduce the number to 0? Something like that. It's not suitable for finding this shortest path. Breadth search always guarantees the shortest path if on a unweighted tree, because look, each move, +1, subtract 1, cost is the same, uniform cost, the same cost. So it's unweighted graph. We can find the shortest path in an unweighted graph, unweighted or uniform weighted graph using the breadth search. Okay? Okay, that's it for today. Bye-bye.
Bye.
Bye.